We're talking a little bit about static pressure, just some basics. It's a topic we talk about a lot, like the basic refrigerant cycle, and but it's a good one. Before I even talk about the different types of tips, not that you're going to necessarily get confused, but it is important that you don't get the terms confused. Two primary different types of manometers that we see. So the first one is the type of manometer, well actually, how do I want to separate this out? There are two main types. The first one is what we call the utility manometer, or just your regular old service manometer. And that's like the field piece, whether it's a single port or a dual port. We'll talk a little bit about that. But it's the field piece and Testo and whatever other UEI, whatever other brands you have. And those are designed to measure in the inches of water column scale. Okay, so we'll start there. Inch of water column, what is it? Anybody know? Inch of water column, Sam?
Measurement of water column.
Measurement of pressure. It's a measurement of pressure, right? And it's a smaller measurement than a PSI. We don't even need to get into the specific units, comparing units. It's a smaller measurement than a PSI. So when we're measuring air pressure within a duct system, or whether that's static pressure or velocity pressure, or whether we're measuring gas pressure on a gas valve, we're typically going to use the inches of water column scale. Okay, so you're not generally going to use PSI for that. But there's also a smaller scale than that we sometimes talk about, and that is called the Pascal. So the Pascal is a much smaller unit of measure, and we use the Pascal for things like a blower door test. Anybody ever seen Max do a blower door test before? Anyone here seen that? So that's when you actually depressurize a house and then you measure the leakage rate of the house. You also will use the Pascal scale when you're doing things like duct leakage or things like that, where you have to measure really, really tiny amounts of pressure. In order to measure in the Pascal range, you need to have something called a precision manometer, or generally speaking, they're a blower door manometer. It's a really expensive manometer. Recently, the Energy Conservatory, TEC, came out with a much less expensive version, which is a single port version of a precision manometer called the DG8, which is pretty revolutionary. Those of you who were in the class where we talked about the true flow grid, where we're measuring airflow directly in the system, that uses a DG8 manometer. And a few of you here have a true flow, right? But anyway, so those precision manometers are necessary for things like blower door tests, or for doing things like room depressurization testing. So as an example, Max and I went to a house recently, and one of the questions was, does this room have the proper amount of supply and return balance? Okay, have you ever wondered that before? Does this have a balance of supply and return in a room? Well, it's really easy to measure if you have a precision manometer, because all you do is you just shut the door to the room, you put the hose underneath the door, and you measure the pressure differential, because the manometer is measuring wherever it is, and then the hose is measuring the other room. And that pressure differential in Pascal should not be greater than 3, which is still such a tiny measurement that your regular Testo or field piece or UEI manometer wouldn't even pick it up. So it has to be a really precise manometer for that. And that really is the best and easiest way to measure whether or not there is a return to supply balance in a room. Otherwise, you would have to actually take a flow hood and measure the return versus the supply to see kind of where you stood on that. But when you have passives, especially, the goal of passive returns or any sort of return pathway is just to make sure a room doesn't pressurize. We don't want a room pressurizing up without the air being able to return back, because then otherwise that results in reduced airflow because there's back pressure against the vent, and it also can result in losses because that air tends to leak into the unconditioned spaces. Go ahead, Bert.
Yeah, I was finishing your sentence.
Were you?
Yeah.
That's nice, thank you.
Pause.
I appreciate that. I wanted to kind of get that out of the way, two different types of manometers, but then for the stuff we're talking about today, which is measuring static pressure, there's also two different kind of subsets of the utility manometer. The one is the dual port manometer, and the other is the single port manometer. So the single port manometer would be like these little field piece job link probe manometers. And with these, the way they work is you zero them out initially before you connect them. So you zero them. Generally, you're going to zero them with the hose already on it and everything, so that way you're not changing anything. You zero it out and then you take the measurement. So it relies on that accurate zeroing measurement initially in order for you to take a proper measurement. When you have a 2-port manometer, in most cases you're measuring a differential pressure, which means that you've got the manometer in the space and it's measuring the pressure in the space, and then you're using the other port to measure whatever pressure reading you're measuring. So for example, if I'm going to measure my return static in my system, I want to measure the return pressure in the system, I have my manometer in my hand, it's got an open port, and then I take the negative side and I hook that into the return, and that shows me what the return pressure is in comparison to the differential in the space, which is nice because you don't have to zero it because it's all automatically zeroing because it's not measuring a single pressure, it's measuring a differential pressure. Simple terms, there's only really 2 ways to make a pressure measurement. Either it's a differential pressure or it's a zeroed pressure, which is still a form of differential pressure. It's just making a pressure measurement to something that occurred in the past, a zeroing out. So you zeroed it out and you said, all right, here's my baseline, and now here's the pressure measurement. And the reason why that's important is that the pressure in the room doesn't stay the same. Have you ever seen, like, if you look at the weather, it shows barometric pressure, and it shows how that changes, right? So pressures are always changing, even at sea level. Now, obviously, if you went different, you went to a different elevation, then obviously the pressure would change. But pressure changes regardless. It can change because there's a wind blowing on one side of the home, so that can pressurize particular rooms or particular spaces. So those are things that can impact a pressure measurement, and you have to have that true zeroing. Okay? So I know that was a lot. Is there any other way you would like to say that, Bert? I know I just spouted a lot of information. Is there any other way?
Go to check static pressure. Just zero it out right there.
Right.
When you're in. Don't rely on yesterday's zero.
Correct.
All right.
That's the main point. And that's also true if you're going to use a set of gauges, for example. You need to get it to 0 atmospheric pressure, zero it out before you take a pressure measurement, which is really important with digital gauges because in some cases you may have, let's say you have ball valve hoses or something, and you've kept a little pressure in there. That can really mess with your measurement, especially if you zero out to pressure versus zeroing out to atmospheric pressure, meaning you zero it out and there was still pressure in the hose, as an example. That can really throw your measurement off. Make sense? So every measurement is kind of a differential pressure measurement. It's just a question of what it's comparing it to. Is it comparing it to a real-time atmospheric measurement, or is it comparing to some measurement that you zeroed to previously? Does that make sense? It's always measuring against something else. And again, the reason that is that there is no such thing as zero pressure. Like what we call zero pressure is actually just 14.7 psia thereabouts, but even that fluctuates. So if we're not zeroing things out regularly, then we're not going to be measuring an accurate pressure, which matters more when you're doing a precision manometer reading in the Pascal range than it does when we're measuring in inches of water column, and even less when we're measuring in psi. Because as you are measuring a bigger number, things like barometric pressure make less difference. As you're measuring a smaller, finer number, things like barometric pressure and wind and all that can make a bigger difference in your measurement. All right, I just wanted to kind of get that out there. It's a little bit more advanced. But let's start with just making sure that we understand the difference between these two things. A lot of people will call a static pressure tip, a lot of people will call it a pitot tube. It's not a pitot tube. Has anybody ever heard that before, pitot tube? Pitot tube is actually a tube within a tube. So whenever you see a pitot tube, there's actually going to be a port on the side and a port on the back or on the end. And how a pitot tube works is that it takes a pressure measurement in the end, which is both a combination of the static pressure or the balloon pressure inside the duct, plus the pressure of the force, the directional force of the air, right? So if you imagine if I'm in a space and it's got a breeze blowing, or it's got like a fan blowing within the space. Let's say I take a fan and I set it right here in the space. Now that fan isn't affecting the overall pressure in the room because it's just taking air from the room and it's moving back into the room, right? But it is creating a directional force. And so I could measure the force of the air molecules going this direction with a probe pointed at the airstream. But that's not static pressure because, again, it's just recycling the room. It's not changing the overall force against the walls in the room. Does that make sense? So what a pitot tube is designed to do is to actually measure airflow, actually measure air velocity. And so what it does is it takes the total pressure in the end, it subtracts out the static pressure, and what's left over is velocity pressure, or that directional force. And so all you do is you just connect your differential manometer across these. By showing that differential pressure and using a calculation, you can calculate what your airflow is. Now, this is another tool that requires a precision manometer. So the manometers that we use, you're not going to use this. And that's why we never use it, because we don't have manometers on our trucks that are good enough to actually use this to measure airflow. But people like in the building science part of the test and balance sides of our industry, they use this a lot to measure airflow. And that's where it gets confused, because these two look very close to the same, right? But a static pressure probe, it has a closed end and it only has ports on the side. So how do we install it? So when we're taking a pressure measurement, we're putting the probe against the flow of airflow. So we're pointing it against the flow. And why are we doing that? We're doing that so that way those little ports on the side are not affected by the velocity flow, because we don't care what the velocity pressure is. We want to know what the balloon pressure is pushing against all sides. Okay, so here's an example. I would create positive static pressure in this room if I put a fan in the door and blocked off the door and blew air into the room, right? And why would that create positive pressure in this room?
Because it's forcing air inside.
It's forcing air inside from somewhere else, right? So we're taking air, which is just molecules, we're forcing them into the room from somewhere else, and so those are exerting a force in all directions on the room, right? And what happens if I turn the fan around, seal the door off, and blow air out of the room? What happens to the room?
Negative pressure.
Goes into negative pressure, right? Now what does that do on the other side, though, of this? Because we have another enclosed side of the building, what does it do to the pressures on the other side? If I'm pushing air into this room, what does it do to the other room?
Reverse, stops it.
Right, it negatively pressurizes that room and positively pressurizes this room, right? So we're not talking about directional force, we're talking about all directions force, balloon force, right? Like the pressure on the inside of a balloon. So that's what we're doing with the static pressure, with the static pressure probe. Now, what we've learned in residential systems is that the positioning of our static pressure probe really isn't that critical. And the way you can know is you take a pressure reading and spin that probe all the way around, and it doesn't make a massive difference in most cases. Which is why, in some cases, people have taken even using things like ball needles. So that way you can drill a much smaller hole and place the ball needle in. Now, obviously, you couldn't do that in ductboard because it's not going to be long enough. But things like when you're measuring within a cabinet, it's easier to make a tiny hole and place a ball needle in than it is to use a static pressure tip. But if you are using a static pressure tip, the way to insert it is to insert it so that way the tip points against the flow of air. Or with, either one doesn't make much difference, but you don't want it sitting sideways because that can make a little difference in the measurement. Are we with each other so far? So when we're doing a static pressure measurement on an air conditioner, what scale are we using? Start basic. What is the measurement scale?
Water column.
Inches of water column, right? Inches of water column. It's the force is exerted in all directions. The pressure to inflate a balloon. It can be positive or negative in reference to the atmosphere or to another space, right? So when we say to the atmosphere, we're really just saying the room when we're measuring in an air conditioner. But that measurement could be off if, say, the room that we've got our tool in is either positively or negatively pressurized significantly. Now, again, when we're measuring in inches of water column, it's probably not going to be enough to make a difference, but just recognize when we're taking a pressure measurement, it's always in reference to something else. So if we're in a heavily depressurized or heavily pressurized room, that could also affect our static pressure measurement. Does that make sense? Where our tool is. It should be positive and the supply side past the blower, so the blower is the point of pressure change, right? It's going to be negative leading into the blower, and it's going to be positive leading out of the blower. So just looking at the system that's drawn here, what type of system is this? Say it again?
Furnace.
It's a gas furnace. You said a positively pressurized system.
You have the 10 air trains.
Yeah, there are other types of systems that are also positively pressurized. Mitsubishi fan coils would be the same thing. In this particular case, we have positive pressure going through the evaporator coil. So where would we take the measurement if we're measuring total external static pressure? Does anybody know? On a gas furnace, right where we show it here. And does anybody know why? Because when we take a total external static pressure measurement on a fan coil or an air handler, a heat pump system or a straight cool system that's not a gas furnace, we would measure above and below the air handler. Why do we measure below the coil when we're doing a gas furnace? Why is below the coil the right place to measure? you will have a pressure drop, that is true, but the particular reason why we measure it this way on a gas furnace is because in a gas furnace, the evaporator coil is actually a different piece. So, you know, when you install a gas furnace, you have the furnace and then you have the coil, and they come in two separate boxes. They don't come with each other, right? On a fan coil, an air handler like this one here in the classroom, the coil comes in the box, right? So when the coil comes in the box, that means the unit is rated with that coil already in place. Meaning the manufacturer knew the coil was in place, they already know the pressure drop across it, they know everything about the coil. When you take a gas furnace and you stack a coil on top of it, the manufacturer may make the coil, but they don't know what coil you're going to choose. In many cases, there's different coil types that could match with that furnace, in almost every case. So they don't know exactly what the pressure drop is going to be, so when they give you a static pressure rating on the furnace, that static pressure rating does not include the pressure drop across the coil. Does that make sense? So how do you measure static pressure in order to see whether or not you're at the rating of the equipment? You measure what's across what's in the box. So in the case of a fan coil, what comes in the box is the blower and the evaporator coil, right? In the case of a gas furnace, you have the heat exchanger and you have the blower, but you don't have the evaporator coil. So you have to measure the coil pressure drop separately.
Would that be the same for a heat pump that comes as a two-piece system? Have you ever see like certain manufacturers have where the coil and the blower are two separate pieces, you can screw them together?
No, but because I think that's still going to be one model number.
Okay.
So if they come in the same box, or if they come as a match set, where that's the only way that they're going to go together, then it would count as that would be, the evaporator coil would count as part of the fan coil, part of the air handler. So when I say fan coil and air handler, those are interchangeable terms. It's just different manufacturers and different geographies, they refer to both. When you look at a data tag on an air handler, for example, or on the inside of a gas furnace, it's going to have a data tag that gives this rating. It's going to list what the design test static is. So it'll say design static or test static, or it's going to give you a rated static pressure. And that doesn't mean that you can't have a static pressure that's different than that. It just means if you have a static pressure that's different than that, it's going to affect the system's performance, right? So maximum fan speed, this is what the test static is for the majority of systems, but they are not all that way. In fact, if you look at this system, actually I'm not sure about this one, but a lot of systems you're going to find will have 0.2 or 0.3 test statics rather than 0.5, which means that if you have a static pressure that's higher than that, then it's going to perform worse. In the case of a variable speed blower motor, what is it going to do if you install a duct system, install a filter, install whatever, so that way the static pressure that you're actually seeing is higher than the test static? What's going to happen to that blower motor? Anyone know? So what does an ECM blower motor do? A variable speed blower motor, what does it do? Ramps up and ramps down. And how does it ramp up and ramp down? What makes it decide? It's based on, it depends on the motor specifically, but it's going to be based on airflow essentially. Okay, so we can get a little detailed about that with an X13 versus an ECM, but it's really based on airflow. So if static pressure, the amount of pressure that it's working against, increases, what does that blower motor have to do in order to keep that same airflow? Hey, it has to spin faster, right? It has to spin faster in order to keep the same airflow. What do you think it takes in terms of the motor power when you have to spin the motor faster? It goes up, amperage goes up, right? So it has to do more work in order to move the same air. So what are you doing to the system when we install it on ductwork that's higher static pressure than what it's designed for? We're increasing the cost to operate, and potentially, and almost assuredly, we're reducing the life of that motor. So it isn't to say that we can't, in some cases, go above the test static and still be within the manufacturer's kind of, we call it the operating envelope of static pressures that it's designed for. But it is very possible that we may be operating it outside of that, and then we are going to cause premature failure. A lot of times, these consistent motor module failures that we see on certain systems, a lot of times it has to do with static pressure, which is why when we do a motor module replacement, when we get done with that, because obviously you can't test static pressure until you replace the module, you should definitely check the static pressure. Now let's be practical about this. Can the static pressure that the blower motor sees, can it change over time? So you install a system and it's one thing, over time it changes, right? What causes it to change?
Equipment gets dirty. Customers bad about filter changes.
Filter changes, evaporator coil, right? Those are things that cause static pressure to go up. Now, when we're measuring total external static, we're measuring outside the box, right? We're measuring underneath the unit, generally speaking above the filter, and we're measuring in the ductwork. On an air handler, what doesn't that count? Evaporator coil, right? That evaporator coil gets dirty, that blower is increasing in the amount of static pressure that it's seeing, but we're not measuring there, right? We're not measuring our static pressure right above and below the blower. But can we? The answer is yes, we absolutely can. And we can look at what our pressure drop is across our evaporator coil quite easily. All we do is one probe below, one probe above, right? You measure that differential in pressure from top to bottom of that evaporator coil, and that's going to tell you what that pressure drop is. Now, we would have to know what it's rated for in order to know whether that's good or bad. But you can tell pretty well, like for example, if you've got a total external static design of 0.3, say, and you've got 0.3 pressure drop just across your evaporator coil, that indicates that there's a problem with that evaporator coil. You can kind of use some common sense even if you don't have rating data there. So for those of you who are like, I have no idea what he's even talking about, here we go. This is showing two separate manometers, but it could be a dual port manometer. You would connect one side, the negative side, and either you do that by setting up your manometer in the case of a dual port like this, or it has a negative and positive on most dual port manometers. You connect the negative side underneath the evaporator coil. Now again, this is where it gets a little hairy because here we're kind of showing it below the filter, which would be the case in a brand new system where it's rated with the filter that's in it. But in most cases, we're going to measure above the filter. Because whether you measure below or above the filter makes a significant difference, right? The closer you get to the blower on both sides, the more accurately you're going to see what the blower has. But again, on a heat pump, fan coil, or air handler, we don't really want to measure here because our rating is based on what's measured here and what's measured here. But if we measure below the filter and that filter is really clogged, that's going to make it look like we have better static pressure than we do. There's kind of an infamous video, I don't know if you guys remember this, but there's kind of an infamous video where a guy was showing how a pleated filter, a really high MER filter, the system actually has lower static pressure with a more restrictive filter, right? He was showing that see, it should even work better, but that was because he was measuring below the filter rather than above the filter, and that makes a big difference, right? Obviously, if we're measuring our pressure here and we have a dirty filter, here, our negative pressure is going to actually be lower, because now we've reduced the airflow, and so that drops the filter in the duct. Drops the pressure in the return duct. We have to measure above the filter to see what that actual pressure drop is. And again, you can do the same thing. You can put one probe above, one probe below, and then see what that differential is in order to really see what your filter static pressure drop is. And again, just use some common sense. If you've only got 0.5 to work with total across the entire system, then having, say, 0.2 across your filter alone, that's a problem, right? It's too much. So generally speaking, across our filters, we want to keep that pressure drop even below 0.1. Anyway, this is showing how we would get to this number. So here we're showing a supply of plus 0.25. We're showing a return of negative 0.25. That equals an external static of 0.5 total. Make sense? Any questions about that? So again, a couple things, we've talked about this a lot. We've actually kind of maybe talked about this too much. But in order for us to even have an accurate measurement with a manometer for static pressure, we have to first make sure our system's producing the proper airflow. And in order to do that, first it has to be on high speed. So if you've got a 5-stage system, it needs to be on 5th stage. It needs to be all the way ramped up, right? It can't be in dehumidification mode. If it's in dehumidification mode, that blower is going to be ramped down, right? And it has to be set up properly. So again, if we don't have the taps correct, if we have it set on the wrong tonnage, or inside our infinity controller or whatever, we have some settings set up wrong so it's not producing full airflow, then static pressure is meaningless. Because again, what is the static pressure on a system that's not running? Zero. And that's a nice low static pressure, right? So it should run great. The point is that unless it's running at full airflow, static pressure doesn't mean anything. So we've got to make sure that it's doing that first. And a lot of us will rightly ask the question, how do I know if it's producing full airflow? And the answer is, you kind of don't. You measure, you double check everything. You make sure that you have the correct calls in the case of a 24-volt system. And then you're kind of stuck with using something like the TrueFlow grid to really know whether or not you're producing the right airflow. So again, whenever we talk about checking airflow, is checking static pressure checking airflow? What is checking static pressure? It's checking static pressure. You're checking the pressure in the duct. It's like saying, it would be like saying, I checked refrigerant flow on the system when you check the pressures, right? Because you know that when you hook up to a system, you've got pressure there even when the system is off. So does that fact that you have pressure tell you that you have flow? No, in the case of an AC system. So the point is that this is not a flow measurement, this is a pressure measurement, and if everything else is the way it's supposed to be, then it means something. But if it's not, then it doesn't. Make sense? So for those of us who aren't in the habit of measuring static pressure regularly, I know a lot of us aren't. And again, I'm not one of these guys who says, hey, and every time you change a capacitor, clean a drain, you need to check static pressure. It isn't a stock practice that we do every single time we touch a piece of equipment. I find that to be overkill. But when you do certain things, it is valuable. So when we commission a new system, meaning when we install it, we do the startup, we're testing it. I want us measuring static pressure on it every time. It can tell us whether we have potential duct problems before we walk away from that. I know it's one of those ones probably when you're in a hurry, job gets late, sometimes it gets missed. But if you know that you've been missing it, you haven't been taking it seriously, please move back into doing it. It's not a hard measurement to take at all. Aaron and I went through this in the past. It really is. There you go. So it is. It's an easy measurement to take, and it has a lot of significance on a startup. You're doing something like replacing a blower motor, because one failed. Now's a really good time to go ahead and check that. You have an airflow problem with the system, or you have a system where you are running something like low superheat and low suction pressure. So it's an indication of low airflow. Now's a good time to check it. But again, I don't want us just checking total external. I want us checking supply, and I want us checking return, because it can tell us where the problem is. When we measure those separately and then we start to measure across things, we can say, hey, this filter is restrictive. I know it's brand new, but it's causing too much restriction because the static pressure is too high for this system. We can do things like measuring across our evaporator coil, especially on a gas furnace, to see, is this too restrictive? Because a lot of people have asked, like on a gas furnace, how do you know if a gas furnace coil is blocked? It's really tough to know. It's hard to get in there and see, right? It's hard to get to see the underside. This isn't something we do a lot, but the easiest way to do this is to make a penetration, a tiny hole between the furnace and the coil, usually at the top of the furnace. There's whole videos on how to do this, any of you who have never done this before. And you take a measurement from the bottom of the coil to the top of the coil, and now you don't have to take it apart to see, is this coil restricted? Make sense? Because that coil is going to have a rating on it if you go back to the manufacturer's data. Now, a lot of this gets a little arduous because you got to go back to product data and all this, but in some cases, it's going to be the best way to solve a problem. So again, this is just showing measuring across an air filter and a rating on an air filter and measuring across the coil. A lot of times, a filter is going to actually give you this data, and so it's going to show you with a certain CFM running across that filter what the pressure drop is going to be. In fact, I think this one is I think this is like a 16 by 20. I think this data comes off of a filter that I put in my own house, a MERV 11 filter. And you can see that even at like very small airflows, something that you're going to see on a 2-ton system, you're going to have unacceptably high pressure drop across the filter. Which just goes back to the whole idea that filters cause a lot of problems because we get in the mindset that if it fits, it flies. Meaning, well, the filter fits, that means it's a good filter. It fits underneath the air handler, it fits underneath the furnace, it fits in the duct, so it's the right filter. Just because the filter fits doesn't mean that it's not going to have excessive pressure drop across it. Especially with 1-inch filters that are really, really dense, they cause a lot of pressure drop. That's why we like to go to bigger 4-inch filters, make them as big as we can. If we can put them in the return riser, we put them there and kind of flare out to the bigger size because it's a lot less pressure drop when you have more surface area. The more surface area, the less pressure drop. And the better it filters, and the longer it lasts. So it's like a super cheap win-win-win-win. So those of you who are installers or service techs, and maybe you'll see somebody who's doing sales and they're like not paying attention to it again, remind them like, hey, this should go in the return riser because we've got room to put it there, and we can put a bigger one in. We don't have to put it under the unit. And especially in cases where we can put a media filter on installs, we need to put one. We should not be just doing a 1-inch filter. It shouldn't be an option. It's just such a great value for what you get, so much bang for the buck in terms of long-term costs, because it's not going to have to be changed as much. In terms of filtration, it's going to catch a lot more. In terms of static pressure drop, it's going to be a much better filter over the life of it, right? Besides the fact that, if you've ever noticed, most filters that go into like our carrier filter racks, they're not really well sealed around the filter. Have you noticed that? Like when you put them in the spring and all that? So what good is a filter when like 20% of the air is bypassing around the edges? The answer is 80%. Better. And the dirtier it gets,
the more bypasses it.
All right. The dirtier the filter gets, the more air bypasses the filter. And so, like for example, if you ever have, this is just another side note in terms of filtration, if you ever have a filter installed in a return air grill and you notice that it's kind of loose, go ahead and use some masking tape. I wouldn't use duct tape because it'll leave residue all over the place, but you guys should have masking tape on your trucks anyway. By the way, if you don't have masking tape, everybody should have it. It just comes in super handy for a lot of different things. Use that masking tape around the edges just to seal it in place so that way air isn't going to bypass. It's a simple thing, but it makes a big difference. So goal is measuring static pressure when there's a reason to do so, knowing how to do it properly, knowing the different types of tools. And again, I do want us to start using, I was actually talking about you, Aaron. I do want us to start using the True Flow Grid and the DG8 more often, both installers and senior service techs, because it is a really nice tool for measuring total system airflow, but also for doing things like measuring whether or not you have a room that's pressurizing, whether the return and supply is balanced, that kind of thing. Very handy. Yes, it does. They do all the smarts for you, but you still feel like you really got it. Yeah, this is good. This is good. Anything to help with self-esteem. We're in the self-esteem business, Aaron. All right, thank you all.
Thanks for watching our video. If you enjoyed it and got something out of it, if you wouldn't mind hitting the thumbs up button to like the video, subscribe to the channel, and click the notifications bell to be notified when new videos come out. HVAC School is far more than a YouTube channel. You can find out more by going to hvacrschool.com, which is our website and hub for all of our content, including tech tips, videos, podcasts, and so much more. You can also subscribe to the podcast on any podcast app of your choosing. You can also join our Facebook group if you want to weigh in on the conversation yourself. Thanks again for watching.